Welcome to Functions, Day 6. Today we're going to look at first and second derivative tests for functions. So this first part here, the first two boxes are just the review of what we did last class, where we looked at where the first derivative, when it's equal to 0, those are called our critical points, and those represent a local maximum or a minimum possibly, and that's a lot of the time. We know that when that first derivative is greater than 0, which means positive, that the graph is increasing from left to right, that the slope is positive. We also know that when the first derivative is negative, then the graph is decreasing from left to right, or that the tangent line slope is negative. So we're going to be using these ideas to identify from an equation whether a graph is increasing or decreasing. We've done a lot of looking at graphs and saying, oh, it's increasing from this value to this value, right? But when we have just an equation and not a graph, right, we're going to be able to now identify those features. Same thing with the second derivative. So when the second derivative is equal to 0, that's going to represent our inflection point. So before, when we've looked at graphs, we've had you just kind of guess where the inflection point is. That is no longer. Now you can actually find the x value of the inflection point, which is pretty cool. And then we know that when the second derivative is positive, then the graph is going to be concave up. And when we know that it's negative, then we know that the graph is going to be concave down. So we can identify a lot of features just from the first and second derivative. So if you look in this last box on this first page, we kind of go through the steps for determining how do we know where the function's increasing and decreasing, how do we know where it's concave up and concave down, just from an equation. So our first step is going to be to find the first derivative and set it equal to 0. And then we're going to solve that equation to find those critical x value points, okay? And so those points could be where we could have a local max or min, right? And where we have a max or min, then on either side of that would be whether it's increasing or decreasing. We're going to put those points on a number line and then find the intervals where f prime of x is positive or negative, and use those then in step 3 to determine where it's increasing or decreasing. Right, so where the first derivative is positive is going to be increasing, first derivative negative is going to be decreasing. Okay, so we're going to do all that first derivative. Then we're going to do the second derivative. So we're going to take the derivative of the first derivative, set that equal to 0, and that's going to give us our inflection points. We're going to put those inflection points on a number line and find the intervals where the second derivative is positive or negative, and then use those to determine where the function is concave up or concave down. So those are kind of our steps that we're going to go through, and I'll go through the two examples next.
Alright, so our first example is g of x equals x to the third minus 2x squared minus 4x plus 5. Alright, so find the critical points of g of x by finding where g prime of x is equal to 0. So the first thing we have to do is we have to find g prime of x. So we are going to do that by using our power rule that we learned a couple classes ago. So this would be 3x squared, and 2 in front, so minus 4x, and then minus 4. And then we're going to set that equal to 0. So 0 equals 3x squared minus 4x minus 4. Alright, so all we have to do at this point then is factor. So factoring should not be something that's too painful at this point. If you need to do the x box, you can do that, but it should factor into 3x plus 2 times x minus 2. X multiplies to negative 4, 2x minus 6x is minus 4x, 3x times x is 3x squared. And then just back to algebra 1. This is actually what I'm teaching in algebra 1 right now. We solve out each equation. So x is negative 2/3, and x is equal to 2. Okay? So those are our critical point. So that's where we're saying that this graph is going to be changing from increasing to decreasing. Okay, so what we're going to do is we're going to take those points and we're going to put those on this number line. So I'm going to put a negative 2/3 here and 2. You do have to put them in the correct order, from negative to positive. And then determine where g of x is increasing or decreasing. So how do we know that? Well, this is the same, so this is just like we did number lines before. So if we look at 3x squared, that's our leading term, right? Our leading term determines the end behavior, right, of our graph. So if our leading term is a degree 2 polynomial, right, we know it's going to be the same, symmetric, and since the coefficient's positive, they're both going to be up. So the right side is going to be going up to infinity, the left side's going to be going up to infinity. So that's the same thing here. So right's going to be positive, and then it's going to alternate positive, negative, positive. Okay? So our first derivative is positive from negative infinity to negative 2/3, and then from 2 to infinity. So where it's increasing then is where we're going to have positive. So it's going to be increasing, and we're going to use our interval notation. So we're going to say from negative infinity to negative 2/3, and then from 2 to infinity. Where it's decreasing is where f prime of x is negative, right? So it's going to be decreasing from negative 2/3 to 2. Okay. So this is kind of the quickest way to do it. Kind of a long, painful way to do it would be to pick values, right? If you picked 3 and you plugged it into the first derivative equation, would you get a positive or negative number, right? If you pick 0 and you plug it in, right? So you could pick different values, but if we kind of have this leading term idea, it makes it a lot quicker and a lot easier, I think, to just kind of get to what it's positive or negative. All right, so if a function changes from increasing to decreasing at a critical point, then there's a local max. If it changes from decreasing to increasing, then it's a local min. So you can kind of, that makes sense, right? Kind of what I do with this is, so if I want to find which of these critical points is the max and which is the min, I kind of look back at my part B here. So I know it's increasing because it's positive, then it's going to decreasing, right? And then it's going to increasing. And kind of what I do is kind of just draw a picture in my head. So I say, well, it's increasing, it's decreasing, it's increasing, right? And so this would be at the negative 2/3 value, and this would be at the 2 value. So what this tells me, right, so I'm just a little bit more visual. If the definition is all you need, you don't have to draw a picture. It's just kind of my way of visualizing it. So I would say, okay, well, this negative 2/3, that's the top, right? So I would have a local max, right, and an x value of negative 2/3, and I would have a local minimum at an x value of 2. So it's just kind of using this idea of where is it increasing and decreasing and telling us that those critical points are the local max and min. All right, our next step then is to determine where g prime of x is equal to 0. So first thing we have to do is find g double prime of x. Sorry, I think I said that wrong before. So we know from above g prime of x is 3x squared minus 4x minus 4. Well, to find the second derivative, you just take the derivative of the first derivative. So we're just going to use that same power rule. Bring the 2 in front. 2 times 3 is 6x. And then we just have the minus 4. Right? So our second derivative is 6x minus 4. We set that equal to 0. Right? And we solve that equation. Add 4. Divide by 6. We get x is equal to 3/2. Right? So this is where our inflection point would occur. That's the x value. If we wanted to find the y value, we just go back to the original equation and plug it in. But at this point, then plot the inflection point on the number line. So we only have 1, 3/2, and determine where g of x is concave up and concave down. So again, I think kind of the easier way to think about this is to think of it in leading term, right? The leading term is 6x. It's odd, so it's going to be opposite. And 6 is positive, so the right side is going to go up, the left side is going to go down. Okay. Again, if you don't like that, it doesn't make sense, pick a number, plug it into the equation, right? So a number bigger than 3/2 is, let's say 5. That's an easy one. 5 times 6 is 30. 30 minus 4 is 26. Definitely positive, right? Here, pick a number less than 3/2. 0. 6 times 0 is 0 minus 4, negative 4. Okay. So if you don't like kind of my shortcut, there's lots of other ways to do it. But what this tells us, though, is where it's concave up is where it's positive on the graph, right? So it's going to be concave up from the interval of 3/2 to positive infinity. And then where it's negative is going to be where it is concave down. right? So from negative infinity to negative 3, to positive 3/2, sorry, it would be concave down. All right, I'm going to go ahead and go on to the next page then. Okay, so find the critical points of h of x. So the critical points, right, is when our first derivative is equal to 0. So our first derivative from our equation, so would be negative 6x squared plus, that'd be 18x, right, plus 168. Right, so we're going to set that equal to 0. Right, and then we have a trinomial, so we're going to have to factor. Now this one, right, we have some big numbers, right, maybe it's not too exciting about, not too excited about factoring that. But one thing you might look at first is, do you have a GCF? Like I know 18 divides by 6, and if I check on my calculator, I'd say 168 divided by 6. Oh, that's a nice number, that's 28. And I'm also going to take this negative out. So I'm going to take the negative 6 out, and that's going to leave me with x squared minus 3x minus 28, right? And now that's super easy to factor, right? I don't have those big numbers. Two numbers that multiply negative 28 to add to negative 3 is negative 7 and positive 4, okay? Remember, if I just have a coefficient of, if I just have a constant in front, I can ignore it. So I just say x minus 7 equals 0. X plus 4 equals 0. If I have to take an x out, that's different. Then I would have to set it equal to 0. So these are my two critical points, 7 and negative 4. So I'm going to put those on my number line here. Again, put them in order. Then determine where it's increasing and decreasing, right? So again, I like to look at that leading term, negative 6x squared, right? So that means that it would be down, down, negative, negative. So negative, positive, negative. Again, if you don't like that, pick some values, plug it back into the equation, see what you get. I just think that's more math than you need, and you can get bogged down in this number manipulation. All right, so where it's increasing, right, is where it's positive on the graph. So that's going to be from negative 4 to 7. And then where it's decreasing, right, it's going to be where it's negative on our graph. So that's going to be negative infinity to negative 4. And then from 7 to infinity, okay? Again, interval notation, and we're using all open brackets because these are our critical points, right, where it's neither increasing or decreasing, right? Because that's going to be where our local max and min are. Again, so this time we're going decreasing to increasing to decreasing, okay? So we're going down, up, down, okay? This is negative 4, this is 7. So in this case, I have a local minimum at negative 4. I have a local max at 7. Okay, so now we have to find the second derivative. So let's write down, I'm just going to write our first derivative down since it's way up above and we can't see it anymore. So negative 6x squared plus 18x plus 168. So if I take the second derivative, right, 2 times negative 6, negative 12x plus 18, I set that equal to 0. Right, subtract 18, and then I'm going to divide that by negative 12, and I get x is equal to 1.5, or 3/2. How you want to write it, okay? So that is where my inflection point happens. Pretty cool. So here is my value. Again, I like to look at the leading term. My leading term in this case is a negative 12x, right? So it would be like this. So negative, positive, so positive. Again, if you don't like that, pick values, plug it in. You're not going to hurt my feelings. So I know it's concave up, where it's positive on the graph, right? So from negative infinity to 1.5, and then concave down, where it's negative on the graph. So that's going to be from 1.5 to infinity. And look at that, we got it all done in under 15 minutes. Yay, super exciting. So at this point, I would suggest doing the homework problems first before you try the daily assessment so you get some more practice with those. All right, have a great rest of your day.